Welcome. We're going to introduce a couple new components, electrical components, and that is the multiplexer and the demultiplexer. So a multiplexer is something that takes multiple inputs and combines them into a single output. Kind of helps you select which input you want to use. This PowerPoint will be posted for you to look at later. I'm going to kind of scroll through fast, but the next picture actually makes more sense almost to look at first. Alright, so here's just a common example. Think of, having a receiver in your family room or somewhere, media room, that you can kind of control what's going to output to either maybe say the TV display or to the sound system, etc. You've got multiple components, right? You may have your Xbox, your PlayStation, your Roku, your whatever. Here they show some examples, right? These are all being kind of sound things. But you've got your multiple sources, and you want to choose which one is going to come out of the system, speakers, video, etc. And so that's what the multiplexer does. You've got inputs that allow you to select which input you're going to use. With two inputs, okay, digital inputs here, these are binary counts, we can count from 00 to 11, which gives us 4 different possible inputs to choose from. So the number of inputs here, okay, that dictates how many inputs you have. I don't know if I spoke backwards there, but the number of selector kind of pins. If I go back to this slide, notice they say kind of N. You have 2, and then the number of inputs you can have will be base 2 to that power. So 2 squared is 4, we can have 4. If we have a third select line, then we can count in binary from 000 to 111, which we know is counting from 0 to 7. That's 8 different options, and 2 to the third power is 8. Okay, so as you add a select line, you're adding, kind of doubling the number of inputs you can have. Here is a schematic of kind of what's happening inside the multiplexer. Here's a waveform. I'm not really going to spend time talking about this yet. It's something that we do want to hit on at some point in the year, so we can kind of start to make sense of these graphs. And here's a kind of a pin diagram. So a 4 to 1 mux, that's 4 inputs being sent out. You've got your inputs 0, 1, 2, 3. You've got your pins to select between 0, 1, 2, 3, that's A and B. So that's going to be where you count binary 0, 0, 0, 1, 1, 0, 1, 1. And you do have to kind of, it's almost like turning on or off, but you have to enable the multiplexer to be working. Okay, if it is not enabled, then you won't be sending an output signal. So you can almost think of it as like a power button, kind of make it effective or not. Notice that little looks like an O or 0 right there on the pin. That is because this has a built-in inverter. Okay, and so you actually need to send ground. That'll invert to a 1 to enable. So this enable's got to be grounded. Your output, you have both kind of the output and the inverted value in the output available to you. Alright, what's a demultiplexer? This is the opposite. This is where you have exactly one input, but you're sending it out to multiple outputs, and not at the same time, but you'll get to, the demux will get to choose which output you're going to send it to. So a good example is a computer connected to, say, a range of things where you might print to. Maybe add a 3D printer, to in here. So maybe you've got a copy machine or some kind of black and white laser copier printer you could potentially print to. You may have a fax machine, a color printer. You may have a big, large format printer, often called plotters. And so from the computer, you're trying to send out, this is the one input, and we're trying to send that out, but we want to be able to select between which printer. So think of that as a application of the demux. And then they give us the same information here again, kind of the logic circuit, the wave diagram, and then here are the pins. Okay, I had to pause briefly there to take care of my dog who was going nuts, barking at somebody outside. So the Demux, you can see you've got one input. It does have an inverter on it, and then you've got your 4 different outputs, and then you've got your pins to be able to select. Again, adding another select pin allows you to count further in binary, so it kind of doubles the number of outputs that you can have. Okay, so a common application and an application that we're going to look at goes with what we just started learning about, which were the 7-segment displays. So believe it or not, we look at signs all the time that are built with these 7-segment displays. And if every single LED was turned on at the exact same time, you'd have to have enough current or power to power all of those LEDs. If instead of lighting them all up at the same time, we could just light up some of them and kind of alternate which ones are lighting, you know, instead of potentially, let's say with like 4 digits, and you got 7 LEDs within each one, right? So you got 7 times 4 is 28 LEDs that you're trying to light up. It's relatively speaking, that's a lot more than if you only had to light up, you know, at most 7, or, you know, with a digit not using all the LEDs, maybe only a few. So what happens for an application is that we actually kind of very quickly turn on and off each digit, and we do it so fast that it looks like they're all on at the same time. Okay, so we did learn about these 7-segment displays, and here we've got a common cathode connected to ground at the top, and then all these pins are connected to power, or VCC. They basically just left the pins disconnected if we didn't want to light up those LEDs, and they've kind of permanently decided what letter is going to show up. So you think of a sign that's just going to say, you know, welcome or something. We're not going to have it change. This is just kind of a way to preset exactly what's going to show up. Okay, real simple. So this says simple message, all segments on. Instead of having all of these connected to power at the same time, okay, we could bring in this demultiplexer, and only one of these is going to turn on at a time. Okay, we're going to cycle from one output to another. So the demultiplexer is only going to turn on one thing at a time, right? The selecting pins is where we count in binary. So we're going to count from 0, 0, 0, 1, 1, 0, 1, 1. And as we do that, you're going to see that 7-segment display is connected to the first output, the second one to the second, and so on. You're going to get exactly one to turn on at a time. Okay, in the end, no one's going to sit here and manually want to do that. And so they have added what's called a ripple counter, which is using some D flip-flops, okay, and then a clock signal to trigger those flip-flops. Okay, so this right here is going to count using these two D flip-flops. We're counting in binary with 2 digits, again from 0, 0 to 1, 1. And we did introduce this concept earlier in the year, and it'll come back up again later. Right now we just kind of want to remind you that you can go ahead and create this in Multisim, and you'll have effectively an automatic counter, and you won't have to mess with switches. So it'll count from 0, 0, 0, 1, 1, 0, 1, 1, and then it'll go back to 0, 0. And so you don't have to toggle automatically with the switch, because we could put a switch here and kind of toggle it at our own frequency. You can put this clock signal, and you can adjust the frequency, which is the hertz, to have it do it for you automatically. And what you're going to see is these are going to turn one on, the other 3 off, the next one turns on, the one that was just on will turn back off. So this is kind of the design in the end that you're shooting for. Alright, So kind of walking this out, when you're looking at activity 233, all right, start with kind of the idea of just building a small section of this and testing it. So first, I'd bring in your power, your resistors, and get your 7-segment displays to correctly display the word that you want to display. Okay, here in this example, they've got the word open, and was that that's kind of already shown for you in the procedures. What I'm going to ask is that you change this to become the word help, and that you see they ask you that in number 5 and 6. So we'll call this activity kind of complete. If you can build in Multisim this circuit with the ripple counter to display the word help. Okay, but I'd start with building this part first and just make sure it says help. Okay, you got it right. I'm not connecting the pins or the LEDs inside the 7-segment display that don't need to turn on. Okay, once you've done that, you'll be able to go back and now connect these to the outputs. So I just have some probes just to see the which output is currently the output that's going. And you notice that we've got 3 1s or 3 lights on and a 0. It is the 0 that is going to power. It's the ground. Because this being a common cathode, it's the ground that we need here, not the power. We've already got the VCC, the 5-volt power coming here on this side of the LED, so we need the ground on this side. Alright, so we've got output 0 is going to be my O, so I'm going to go ahead and connect that here. My second LED, 7-segment display, is going to be the second output, or 1, and so on. So let's connect these. Okay, I've got this 74LS155 Demux, and to help you out, you can see that it's in the 74LS family, which is the group TTL 74LS family, and then we find the 74LS155N. Let's undo that change. I had the pin showing up. Okay, A and B are your selecting pins. So these are going to connect back to our binary count, and then I need to connect the power and ground, and that's it. You're not going to use the other pins here for us. Okay, so the ripple counter, you can kind of take a look at and copy this as well. It's the 74LS74N. You're going to find that in the same place, just further up since it's a lower number. And you'll kind of notice, right, I got the clock signal going in, the inverted value output of one flip-flop becomes the clock signal in the next, also becomes the next data value. So we kind of loop that inverted output Q back to D, the data pin. Q is our output, and Q is going on to be our binary count. So the first one goes there. The first one's actually your least significant binary digit. The next one's going to be your next kind of most significant digit. So we kind of go in reverse order of the way binary. So you notice that this first one, that output goes to the probe that's on the right. So because I wanted this to be visible in terms of binary, 0 0 0 1 being 1, 1 0 being 2, 1 1 being 3. Okay, and then it's the output of the second D flip-flop that is the next more significant binary digit, and that's B. Alright, the clock signal, I'll show you where that's found. That's found under sources, signal voltage, and there's a clock voltage is what I'm using. Okay, so that is your goal, is to basically recreate this circuit in Multisim. And then when you power it up, you should see that. See how mine is cycling open, O-P-E-N, you should be able to see that it cycles through. And in real life, what happens is we get this frequency going so fast that it just looks like it's on all the time. Now, on our computers, we've kind of, some people might have a computer that could do this. My computer, at least, I'm guessing the ones that you're using, it is going to kind of cycle through. I played around with the clock rates, and I couldn't get get it to be going that fast or having my screen refresh that fast that it actually looked like that. But there you go.